Hi, this is Sean Murphy of SK Murphy. I'm the MC for today's PATCA briefing on electronic-based hardware product development for non-hardware engineers. You can learn more about PATCA at www.patka.org. We're fortunate today to have a briefing by Carl Angotti, president of Angotti Product Development. Carl has designed hardware-based products for over 30 years in Silicon Valley. Many of these have been with startup companies. The projects have ranged from designing portions of large systems to feasibility studies to simple circuit designs. Mr. Angotti holds a BSEE from Carnegie Mellon, an MSEE from the University of Southern California, and an MBA from San Jose State University. He is a California registered professional engineer. Carl?
Okay, well, welcome everybody. As I said, this was originally focused on persons who had never done a product development before. And so I'm going to keep that as the focus in mind, but I will take questions as we go along to clarify things, or if you have a very short comment, it would be might be helpful for everybody if you have experience in product development. So let's see. Oops. Whoa. Oops. Okay, so I'm going to overview this presentation. I'm going to discuss the complexity of a new product development, which is shortened to NPD, of a hardware product. I'm going to give examples of project planning for a simple to a very complex product. And I'm going to discuss managing the project, and then we'll have it open to Q&A. So, boy, it's interesting. So, in terms of how I'm going to frame this discussion, I'm going to be using a top-down approach. And so, what I mean is, I'm not going to get into very deep into the details unless somebody drives me there. Right now, I'm also considering only a brand new product of development, not a rehash of an existing design or one that's going directly into production. Those are one going directly into production can be quite a bit more complex than I'm describing here, because you're trying to get a lot done in a single pass, and you probably won't make it anyway. But anyway, and also, of course, if you've already done the design once before and you're respinning it, well, that's a different problem, but I'll cover respinning in my talk. So right now I'm talking about a product that starts either at the feasibility or the demo phase as the product target. And so what I mean by that is sometimes a person comes up with an idea, and there's very often a new sensor or something like that that's involved in the product itself. And so we do a hardware feasibility. Sometimes there might be some fancy algorithm or something, but we need to have a hardware product almost always has some sort of sensor input. I presume we can think of ones that don't, but most of them do. Or we're going to have a demo phase where you're going to take the product and you're going to show it to early investors, perhaps, or take it to a feasibility show, something they're showing a new product. And it's a little bit different because it's done a little more formally. So this is an eye chart that, by the way, I'll stop. Does anybody have any comments or questions up to now? I guess not. So this is a bit of an eye chart here, but it's about the best thing I've seen for product development. When I tried to blow it up to make it so it was visible, it cropped off. It says from research over here, and it says to marketing or marketing over here. So, and this particular one shows the proof of concept. Oh, it shows the proof of concept. I'm going to not click the mouse. Shows the proof of concept here, and then branches out. Well, it turns out we're really talking in this particular thing, we're talking about getting to proof of concept and or beyond. But these two branches, the first branch is the mechanical engineering, if you will, branch, where what you're doing is you're talking to customers, but you're just showing them pretty pictures or what have you. And sometimes what you will do is you'll have what's called a wireframe. That's what this is here, which is sort of a mock-up of the product, perhaps created on a 3D printer, or today anyway, or maybe just sketches or drawings or balsa wood models with paper and what have you, which we used to do a lot of in the past. And then what you do is you create a looks-like prototype so that it looks like the final product physically might look. And ideally, it would look pretty close to how it would physically look. Then this goes into what's called, here they have it called engineering prototype. But the other side is essentially you're developing the hardware now, and of course the software, firmware, whatever. So you have an engineering spec, and then you're going to make a works-like prototype. And they show here the feedback loops going through, as sometimes you have to go through this more than one time. And of course, at the very end, you ended up with an engineering prototype, which then you pass into what's called engineering validation, which means does it meet the spec? And then after that, you ideally would have, you're going to have some user or another. So design validation says, does it do what the users or stakeholders want it to do? So any comments here?
Nope.
I guess not. Okay. So I start off with this slide says the complexity of hardware development. And of course, this assumes the development of a new product from the very concept that assumes there is a perceived market for the product. I put this in there in bold because a lot of times I'm working for clients, and in their head they have a perceived market, but they really haven't market tested it yet. But it can be a chicken and egg phenomenon where sometimes you need to build something for people to give you feedback, for the market to give you feedback. But very often people will go quite a ways and spend quite a bit of money before they find out that there's no market for the product. And that's really unfortunate. But I usually, since I'm not a marketing person, I just develop the product that they want, that they have in their mind. But so, and it turns out that most product developments involve the interaction of many diverse skills. And this is one of the complexities of the problem. You have electronic engineers, so there's circuit design. Sometimes you have potentially FPGA, the field programmable gate arrays in the design. I worked on a medical product about 2.5 or 3 years ago, which had 7 FPGA people working there, trying to create an ability to do which today something you do with a NVIDIA chip probably much more easily, although it isn't necessarily easy since that's a very special programming skill that not many engineers have. But you do have additionally, you can have programmers, which include firmware and PC programmers, personal computer programmers, and also mobile software developers. So these are all different skills that if you're going to develop a product, you may need to bring into play. And of course, there's mechanical engineers and mechanical designers. They're the ones who conceive of the mechanical appearance of it and eventually create the mechanical drawings that are used in let's say, the demonstration product. And then there's have to be managers and project managers for the project. And those are the ones that are either the stakeholders or reporting to the stakeholders on the project. And another complexity is there's a number of project interdependencies, each of which have their own risks. And I'll go into that a little bit. And one thing that I've learned through the years, certainly seen a number of presentations by specialists at Stanford, that communication between the skilled persons is very critical to success. And I'll get into that a little bit as I move on here about what that means. So normally, what I recommend my clients do is to follow a defined process. But you can, I have these defined on my website as well. I have a lot of resources on my website. But sometimes people forget critical steps in the process and they get overlooked, and then that creates a lot of problems later on. And so it's always best to at least know that there's a formal process, and one can follow it or not, but at least you know if you're skipping it, you're doing it intelligently. So normal project has several formal steps to completion. So the first is product concept. So that's what comes out of the brainstorming and whatever, and the ideas of the conceivers of the product itself. And then we create normally some kind of initial documentation, which very often defines what is often called a minimum viable product. And then I've added these other ones: minimum viable feasibility product or a minimum viable demo product. Each of these produces something at the end that's a piece of hardware. So I call them a product. When I use that term product, I don't mean something you're going to sell. So basically, and then there has to be a documentation phase, again, of the minimum specs that are required to complete the minimum specs that are required that you're going to design to. And very often they include things like system high-level functional specifications, hardware specs, firmware specs, software high-level specs. Most people don't write too much in the way of software specs anymore, except to describe what it might do. And as I write here, often what's overlooked is initial test and final test specs. A lot of times when products are developed, they don't actually, one doesn't think about the fact that you're going to test this thing later. And the question is, it would be a very good idea, the comment would be a very good idea to have what initial tests you're going to try and achieve, and then what the final tests are going to look like. What are you actually going to test? Specifically, which specs? And as has been mentioned many times by people who work with me and those who are truly interested in this so-called agile methodology, these are living documents, which means that theoretically they should be updated as the project moves forward. Unfortunately, that goal is not often met, and that can create problems later if one's going to move on to the next phase, more towards production. So I'm going to, let me ask, is there any questions about what I just said?
I had a question for you, Carl.
Yes.
So often problems, for example, thermal issues, EMI issues, I mean, there's many, cut across domains or expertise. Have you seen any techniques or practices that allow different experts, different people with different expertise on a team, reach some working consensus or rough consensus on how to move forward? Because when things fall in the seam, it can get tricky, right?
Yes, it can. And of course, that's probably wouldn't get picked up until the demo is completed or the feasibility is completed. But yes, let's see if I can reframe that question in my mind anyway. So you're saying that, let's say if someone has a skill on the team and they know that there's a potential for thermal problems in a particular kind of product.
No, let's
Yeah.
say you've got a thermal problem that shows up in the prototype,
Oh yeah.
and you've there's several ways to address it? How does and some may involve more mechanical solutions, put a bigger heat sink on something. Some may involve introducing a low power mode or using different parts that don't take as much power. Maybe the way the board has been laid out is exacerbating the problem, creating a hot spot.
Yeah, most people that I work with anyway that are developing a product, when that happens, they try to bring in an additional expert to help them resolve the problem. But as you said, if it's something simple like adding a bigger heat sink or whatever, most of the time, probably the design engineer would do that. But sometimes, as you said, the problems can be quite tricky. And so, and of course, there are systems trade-offs, right? Like you said, you can power down the unit to resolve a heat problem. But typically, heat problems are, if you have them, they have to be designed out. I don't think it makes a lot of sense to proceed forward with them at this phase anyway. Any other questions? Okay, well, let me go to the, so now I'm going to start talking about the formal planning process. And what I'm going to start off with is a very simple design. This happens to be a design I've been focusing on lately. It's a design that's made in China and it was designed here in the US. And it's a transimpedance amplifier. It's all analog, it's pure analog. So this will allow me to introduce you to these documents that I've made. And so this is kind of a, I don't know, a monkey business way of trying to do this. But almost all hardware products are designed using what's normally called Gantt charts. These other methodologies don't work very well with hardware. And then what I do here is I show these, I call it schedule block 1, schedule block 2, schedule block 3, etc. And what I'm doing is I'm just trying to show the phase relationship between what's going on. Some of these blocks may be very long in time, some may be relatively short. But if I put everything onto some kind of an example Gantt chart, the Gantt charts become eye charts. You can't read them. So I just wanted to get the point across that, so first you have the brainstorming and market research phase, and then you generate the overall functional spec. That's what it's going to do. And then eventually you will convert that to a project plan, something that's going to say how it's going to be done. And the oops, what did I do here? Oh yeah, you generate a spec here, put together a plan, the basic plan for the project, and then also included in the plan, oftentimes is a mechanical person, even in a simple design like the one you saw there, sometimes requires some mechanical input. Usually not too much if it's just a single PCB, printed circuit board like that. But typically what happens is, the plans put together, the specs put together, then the engineer designs the board. And oftentimes these two persons, the PCB layout person and the engineer might be the same today. So you don't have a new skill added. But very often when I'm doing complex boards, a PCB layout person is also hired. So that's another skill that the engineer has to communicate with. And of course, the engineer has to communicate with a mechanical engineering person as well. And then eventually the unit is fabricated, which means that the parts are purchased and they're put onto the printed circuit board. And then they are checked mechanically to see that they look okay from a fabrication point of view. And then they enter test and debug phase. And then very often, although most people claim that they can do a project even a simple one in one spin. Oftentimes it takes two. And so I just put in here respinning. So essentially, that's essentially the quick repeat of the previous steps. And then eventually, so we respin the PCB, and then we do the mechanical electrical um, uh, uh, demonstration of this particular device. In this particular case, it might be a potential customer, or it might just be people who are interested in early stages of the development of the project. So any comments here?
Looks good.
But the only other thing I can say is that very often this test and debug phase in projects can go on very long. And we'll get to that when I get to the next one. So let me go to the next slide, where this is an example of a more complex design that uses an MCU or microcontroller unit. And so this is in particular, this is a card. It's a plug-in card that interfaces with a Raspberry Pi. And so it is an analog card that through these interfacing plugs can allow you to perform tests where the microcontroller unit is very well defined. And let me get into that when I get to the more complex designs layout. So you can see it gets a little more complicated now. A lot of the stuff is a repeat, right? Like here's the brainstorming market research. Let's hope you've done that. And then we have a general overall spec, and then feeding from that, the mechanical design spec of some sort. And then there's a firmware spec, which again, these are all hopefully very high level specs. And then very often when you have a microcontroller, you have to write some kind of code that runs on a PC. Although a lot of times now I use some of these more modern terminal emulators. And if you write your firmware correctly, you can engage the system directly from terminal, entering data in terminals. And there are a few terminals, terminal emulators that allow you to do things like store the sequences, and then you can recall them to repeat them. Because very often when you're testing the unit, you are repeatedly doing things, and so you want to have some way in which you can do that efficiently. Anyway, and I call this initial coding on the SDK. SDK is, oh, by the way, I'm sorry, I forgot. The user spec on this and on these kinds of designs are, I assume that you assume in a particular design like this, almost always the user is very skilled. That is that they know a lot about what they're doing. They're not like someone that's going to push a button on a computer screen and something's going to happen. These are usually very skilled users when you're developing a demo product like this. So in the meantime, this SDK, which almost every microcontroller that you can buy on the market has what's called a software development kit, which is something like a Raspberry Pi or an Arduino. Recently, I've been mostly basing my products on the Arduino family, but the Raspberry Pi has some advantages to it in that you can put displays on it very readily, and you get a lot of stuff with it. And anyway, so I don't want to get into too much detail about that. But so then eventually, when you get the product hardware tested, you can see down here, this is when you can begin to integrate the hardware, the firmware, mechanical, and everything. And then eventually the next, and remember I said here here is where everything that's gone before comes together, and very often this can really bamboozle damage the project a lot. But in the meantime, when you get through that phase, you now have what's normally referred to as the alpha product, which you can show to people. Very often you only make 2 or 3 such of these things. Sometimes people plan to make 10 of them and they end up throwing most of them away. But you can do it. And if you're very, very lucky and you're able to move forward, you'll have a bunch of products that you can now distribute around to other people, to people like in marketing, to show around. So again, almost always there's a respin in this kind of product. I've virtually never seen it, although I hear people claim they do it. I have never seen it myself, which means you better plan on that. And what you're going to do is, again, you're going to repeat all these steps in this one block here. And then you're going to, I'm sorry, you're going to, essentially you're going to repeat all the hardware development specs, and then you're going to enter the test and debug phase. In the meantime, while this is going on, the folks are going to quickly update the firmware, the user software, whatever. And then eventually this is all integrated together again, which means now, hopefully it's a lot less time here, even though it shows only one block. And eventually you come up with a beta product, which is something you're definitely going to make more than one of, and use it for purposes of showing things to the stakeholders or buyers or whatever. Anybody have any questions about this modality?
Yeah, Carl, could you clarify? You've got a line there in C for, is that how many people or how many time chunks it's going to take?
I'm referring to the time, like it was a Gantt chart. You might have a lot of people involved too, but that theoretically, so-called mythical man month, if you put more people in a project, you will get the project done more quickly. But of course, the communications among them has to be very strong in order for that to work. But it turns out it can be either people or time, but I'm talking about time here right now. Most of the time when I'm working on projects of my own projects, there's usually one of each. If you start getting into complexities like adding multiple people, you can spend a lot of time and a lot of money and come out with nothing. It gets kind of messy. I'll get into that a little bit later when I talk about the problems. That's a good question. So now we're going to go to the most complex design. And this is one where you add a PC and smartphone type interfaces to it. So now, you're just imagine trying to get this in one shot, but a lot of people do. So what happens, let's see what happened. Oops. What happens is you end up with just a lot more stuff going on. And you almost always will be respinning. But the difference here is that you're going to use unskilled users, both on the PC and also on the mobile software spec or mobile software itself. So you're going to be defining it. So now what you've done is you've added even more people that have to communicate with one another as the project goes along, in order to come out with something where you end up with all the integration down here going well. And so you end up repeating, you end up with a mobile spec, a high level spec. Then you end up with a lot of coding. And then of course, firmware, software integration, where you are using the SDK, the software development kit, and you're testing it at that level before you actually have the real stuff. which is right here. And of course, depending upon how well these folks have been coordinating with each other, this can take quite a long time. And most people, you would think in months, very often. Is what I have seen anyway. And we can talk about why that happens. And then of course, I have a quick block here where I say almost always there's a respin for sure here of all kinds, the firmware, software, mobile, everything. And then you end up test and debug, which hopefully is much shorter now because you know a lot more. And then you get mechanical software, everything integration here, which is the longest again, but still likely to go a lot faster now. Then you end up with an alpha product. Very frequently, you end up respinning it again, and then you end up with a real demo product, which is ready to be beta tested. Anybody have any comments about what I just said here? It's just sort of more of the same, just more complex. So now I'm going to talk a little bit about additional complexities, and this has to do with teams. And you know, one of the fascinating things is that a lot of people who are especially first new to developing a product say, "Oh, gee, we can get this done more cheaply overseas." But all the projects, I belonged to Project Management Institute for a very, very long time. And all I know is that the teams having co-location is the fastest development because the communication between the team members is very strong. It's the best approach, but sometimes it can't always be done that way, mainly because of cost. When I typically do a project, the teams are not exactly co-located, but at least they're in a geographical location where team meetings can be put together rather quickly, if need be. Then you have the additional complexity. You say, well, I can't get all these skills. They're too expensive or whatever. I can't bring them all together for some reason. Like I've worked at large companies where people just work in different buildings and communications problems evolve and quite quickly. That's what comes from the infamous them and us phenomenon. Them guys over there don't know what they're doing, or they keep changing the specs or whatever it is. And so there's not as much communication. And then, of course, you have oh, shoot, I got to stop clicking these. So in the US, about the only problem you have, although there are some differences between people from the South and the East and the West, mostly people can talk to each other and they understand each other pretty well. But there's time skewing going on where you have to move the meetings around. So you have to hold them at specific times of the day so that the team can meet. And of course, because of that, the team meetings are less frequent, which means the communication is less. And then, of course, you get the infamous problem that many, I've seen people, they say, gee, the cheapest way is to hire somebody really cheap in, I don't know where, Romania, whatever, Vietnam. There's all kinds of places now, India, where there are cheap teams you can put together. And this adds additional complexity, which almost always ends up lengthening the debug time during that integration phase. So now you have different time zones and they're significantly different. Like in India, it's practically 12 hours skewed. And then you have different languages. People speak different languages. And they appear to understand English, but very often only one or two people on the team understand English very well. And in the meantime, even those folks have, the countries themselves have different customs and social mores. where the idea of nodding your head means you heard the words. It doesn't mean that you understood. And you also have the deal where it's space-saving kind of phenomenon going on. By the way, all this goes on all projects, right? It's more frequent, that's all, and stronger in foreign countries where someone nods their head and they really don't understand. And also the other way is they don't report truthfully to you because you don't want to be embarrassed by the fact that you're not meeting schedule or whatever. Does anybody have any comments about this slide? Boy, am I that clear? Okay, so the next.
Carl, I'll just add to your comment. Yeah, especially like Japanese, for example, if you hear them say, before they say yes, we can do that, they make a little S sound or something like that. It frequently means no, we can't possibly do that, but we're trying to save face for you.
Yes.
They don't want to tell you that what you're asking can't be done.
Whatever, something like that. But I've even seen this happen between American teams. I worked on a project a few years back now where we had a very disparate teams. I was a project manager on it, and the teams were in Russia and they were in England, and they were on the East Coast in Florida and here, and it was a real mess getting everybody together in a single meeting. So you had a lot of individual meetings with different people at different times. But boy, did we have a lot of communications problems with that one particular project. It was with a large disk drive company that has since been bought up by a larger one. And the product was actually put out, but about 5 years later. Okay, let me click here. So if you're following a formal process and you think you're going to move on, let's say things went okay, then it would be really ideal if you cleaned up the document. Oh, shoot. You cleaned up the documentation right at the end of the beta phase. While people are shopping it around and whatever, clean up the documentation. And then if it looks pretty good, you want to make sure that you have when you get to the next phase, you're going to have a production test plan and implementation, which very often is skipped. Now you start getting into volume, let's say you're going to even build 10 units. Often you build 20 to try and spread them around a little bit. It turns out that they have to be each individually tested, and the engineering tests really suck. So not so very often, but more often than not, I've called in to do production tests after the device has been developed, and they've been using the engineering tests to do production tests. It takes forever because engineers have a different idea about what they're trying to accomplish. And of course, you should put together a reliability plan at that point as well. And there are many other formal testing plans like EMI and all these other things, UL, and such, underwriters laboratories. These are all things that if you put out a formal product, you may have to deal with. So what I wanted to do now, is I wanted to just quickly, this is a kind of an ad for me, but I'm going to open up, this is my website here. And and this is the page under resources. You see, it says resources. And basically, I have a lot of papers here. And if you're interested at all in understanding or keeping up with my ideas, mostly about how to develop a product, I've written a bunch of papers, and I also have newsletters. Just click on one of these. Oops. Oh, taking a while. There it goes. So anyway, I have a lot of newsletters that I've written over the years, and they help explain how to do product development. And I spent a fair amount of time on project management because that seems to be one of the major bugaboos is you have to be what's called a subject matter expert. And that's one of the advantages I bring when I go into a project is that I am subject matter expert and even a high level expert in many of these multiple skills that are required. So anyway, oops, what did I do here? Oh, okay. Somehow or another, I got a slide in there. It didn't belong there. So basically, to wrap it up, I've talked about the challenge of developing a hardware-based product, going from a simple to a complicated one. I've talked about a straightforward process for developing a hardware product. I've showed you some generalized examples of schedules, and I've talked about some further resources that you can tap into to learn more about. And then, of course, as goes without saying, you can contact me anytime and I will give you whatever free advice I can give you in half an hour or whatever. And also I have a link to my website. But now is the Q&A time. It's open. Anybody have any questions? Any questions come in on the chat?
No, I had a couple, but I've been talking a lot, so I'm going to let the other folks go first if they have questions. So one thing that I thought was as they say, the fruit of experience, which is sometimes bitter, is the need to keep the documentation for a project up to date. And especially in an embedded project, you've got hardware specifications that may also have configuration or control registers. You've got firmware then that's interacting with that, and then you may have a layer of system software on top of that. Have you seen techniques or approaches that allow these various different kinds of engineers to at least maintain a rough or working consensus on what the design looks like?
Yeah, to me, it's all in the frequency of the meetings and also the co-location. I mean, if they're not co-located, then it requires more meetings. Of course, one thing I've noticed is that when there's a deadline on a project, for example, there's always people are always getting together frequently because there's a lot of activity. But there should be well planned out rhythmic type meetings all throughout the project. And to me, that's just about the best way to keep that from happening. The problem, it seems to me, which is the one that Agile points out so much, is these meetings can go on forever, and people get bored and they want to know what they're doing there, and then they miss a critical comment. And I'm not necessarily clear how to do that, but the best way, of course, is to keep track of have a well planned out meeting and keep track of who's getting bored and keeping people involved in what's going on. And also trying to get people to plan ahead if there is a change in the product, especially in any spec. It should be talked about upfront in the meeting. So if people want to leave, they can do that. And of course, you got the problems today of people coming in with their computers and diddling on their computer instead of paying attention to the meeting and other kinds of things like that. You have to somehow or another have agreements among the team members to actually pay attention when it's necessary. But as I understand it, Agile in one of its formal processes says hold these meetings to half an hour. I don't think you can get enough done on a hardware project in half an hour, but you can certainly hold it to an hour, especially if the meeting is pre-planned by the facilitator of the meeting. Does that make any sense?
Yes, no. And you talked about this was for primarily software folks who might be new to hardware. Are there some common misconceptions that you see new software team members bring to a project? Things that work one way, the physics of software projects is a little different than the physics of hardware projects. One thing that struck me about your Gantt chart is that in most software projects, the undo cost is relatively low for each step, right? But in
Yes,
hardware, at certain points, you're doing the equivalent of kind of like pouring concrete, and you can't, if you want to remove that, it's not taking an eraser to the drafting board; it's taking a jackhammer to the to the site, so to speak.
exactly. Yes, and that is probably the biggest challenge. It's why attempts have been made to integrate agile techniques and what into hardware products, and mostly have been failures. And especially if you're doing a medical device or something of that nature. Um, the uh, I'm trying to think of a good way to say this. The inflexibility of the hardware gets in the way. So sometimes we do a methodology which is called hybrid, where the software is using agile techniques. The firmware, it's a little trickier, but it can be done. Several people apparently have reported to me that they've done it. I do not use those techniques myself personally. I find they get in the way. They're just they complexify these projects which I work on to such a degree that it's not worth it. Um, Even though many other people actually find them useful. I've talked to some firmware people who swear by these agile techniques, but any project I've worked on, you'd swear at them more than you'd swear by them. Any more questions? Boy,
Well, more of a comment. I know that early in your presentation, Carl, you had referred to FPGAs or a form of programmable electronic integrated circuits. That is one, I wouldn't say exception, but a corner case that specifically for digital hardware, that's one where you can very rapidly iterate if you've properly designed the interface between the programmable integrated circuit and something like a microcontroller where the firmware for the programmable integrated circuit and then the software of the microcontroller can iterate rather quickly. But again, that's primarily operating in the digital domain. For analog, there's some high-end techniques for doing some programmable analog stuff, but not very common.
yeah. In fact, I was really excited when someone came out with a programmable analog chip. That company went out of business.
Yeah.
It's really a very difficult problem. Boy, I wish that you could do that.
Yeah, what we used to do is the analog or mixed signal members of the hardware design team would really come up where they were designing a platform, and then they
Yes.
basically worked with the digital programmable integrated circuit team to say, do you have all the buses you need? You plan for some additional pins that you could then reprogram connectivity, et cetera. And then you really did a great job of designing the interface between that digital programmable integrated circuit and the microcontroller, so that once you got that first rev of the board, then the firmware used to program the integrated circuit and then the firmware used to program the microcontroller can iterate very quickly.
Yeah, they can, and that is a way of attempting to speed up a project. I've worked with them, where, as you said, if you're doing interfaces, you might even have several, even simple CPLDs, complex programmable logic devices, which are much smaller, and but they can save a lot of chips. If you're building something. And in the meantime, the FPGAs, when you get into, a lot of times they're like I said, this one company had 6 engineers. When you're trying to do rapid multiplication of vectors and adding them together, the kind of things that NVIDIA chips do really well, it's because they do multitasking. They have like the one I saw, I think the last 128 separate microcontroller units running at the same time, and doing parts of the vector multiplications in different chips and bringing it all together. That's really something else. And I've never worked with any of those. The one thing is they use a hell of a lot of power though, so they're not going to be used in a lot of commercial devices.
Yeah, a lot of times those are kind of things that we used to use for just like getting the initial proof of concept or trying to get
Yes.
all those kinds of things. And then you go back and apply, design for cost or designing for reduced size or all the things that you might need for a commercially viable product.
Yeah, and I never even got into that in my discussion. Yes, you have to, every time you have to keep respinning because now you want to reduce costs. If you want to go into production, you want to reduce costs and test the damn thing. So that's another phase. That's why I wanted to just focus on just the new product development because I assumed it. But I think it was you that said, what the major illusion that software folks have is that hardware is easy. Because you can go buy things. It reminds me of the time I was talking to a guy who wanted to do something with TV, and he said, I can go buy a television set for $1,000. Why is it going to cost me $1 million? Because if you make an ASIC chip, it's very expensive. And a lot of times they'll simulate them or emulate them, I guess you'd say, on FPGAs first, and then move them down into, and they have these methodologies for converting them and what have you. I haven't worked on such a complex project myself. It usually takes a big company to do that.
Yeah, yeah. The one other thing I'd add is in an important but often maybe undervalued part of documentation is, and again, as this talk is kind of geared towards, electronic hardware design for software engineers, is version control, right? You'll have versions of your programmable IC firmware. You'll have versions of your PCBs. You'll have versions of your software for microcontrollers. And many times as you're making changes in one or more of those domains, they only interoperate with either certain versions or ranges of versions. So it's really important that we wasted a lot of time on a couple of NPD projects that I was on where we found out that the issue was we had incompatible versions or not proven compatible versions of hardware and software we were trying to work together. So, as you've got those various domains that are running concurrently, making sure that you have either one-to-one-to-one correspondence documented, or if there's a range of software versions, real important to make sure that the whole team is aware of that.
Yeah, hey, that's a whole other complexity. Even when you're in development, and the methodology that you use to keep track of which is the latest software, which is tested, which has not been tested yet, and all these things. But really, what really fascinates me is that I came to a company that wanted they had an engineer, and he was the firmware engineer, and he got in an automobile accident and was killed. And they went to go pick up his firmware, and it was in such bad, because it was one person, right? It was in such bad shape that they almost had to rewrite the entire code.
Yeah, the hit by the bus syndrome.
Yes, so-called hit by the bus syndrome. And it was really a shame. And there was another case where the guy actually just left, and he just left. And the code was poorly documented, and it was a similar problem. And this problem that we were faced with was, how do we minimally change the code? Could we do that? Which takes a lot of knowledge of a lot of different things, a lot of skill in order to say, hey, this is junk. So anyway, I guess we've hit the end and didn't have many questions. So
yeah, I think to me the two things that are black magic are analog design and firmware design, where you're trying to optimize tight loops. And so you'll have a firmware guy that sits there for a month and comes out with like 12 lines of code. And everybody's looking at him like, well, because it's doing 20 things in parallel at each step, right?
The killer for me has been in the past. I think I mentioned this before. has been using interrupts and then interrupts and interrupt, interrupt, and interrupt, and interrupt, multiple interrupts and hierarchizing them. And something, you know, without a doubt, one of these things will come together in some oddball way and crash the system or cause some defect in a medical product, which you can't have. And you got to find it, and it happens only once every 22 hours or something, you know. And my God, those are just so I personally, when I write code, I try to stay away from interrupts as much as possible because they can be quite tricky to handle if you're trying to just make a demo product, for example. But you know, just tell you the truth, I know a woman who worked at a company that made a medical laser, and she never used interrupts. No, she just designed without interrupts. And she was able to do that. And the product is now 30 years old, I guess, or 25 years old. She retired with the product itself. And it was able to work just fine. So it proves it can be done if you're clever at what you're doing. But of course, the only interrupt was the interrupt timer, right? You had to have at least one interrupt for the timer. I mean, shit, you got to keep track of time, real time somehow. But anyway, shall we call this a day?
Carl, thanks very much for a very thought-provoking presentation. Are you going to make the slides available as well?
I will make anything you want to make available. So
yeah, there was quite a bit of valuable detail on them. So we'll post the presentation and we'll post the slides. Thanks everybody for coming.
Okay, bye-bye. Thank you. Thanks for hosting, Sean. Did a great job.